Hello, good day. Thank you for your interest in this poster. Myself, Darshana Rajput, and this is our poster titled Photocatalytic Carbon Dioxide Reduction by Bismuth Vanadate using Microfludic System under Visible Light Irradiation. To begin with, it is a well-established fact that excessive carbon dioxide emissions by human activities has the potential to dramatically change our environment. These anthropogenic carbon dioxide emissions are implicated in multiple phenomena such as global warming, wildfires, acid rain, and increasing air pollution. As predicted, global carbon dioxide emissions from fossil fuels grew in 2022 to an all-time new high of 36.8 gigatons. This makes it very imperative to find methods to mitigate carbon dioxide emissions and to replace an increasing portion of fossil fuels by renewable sources to meet global energy demands. Now, several methodologies have been demonstrated for carbon dioxide conversion into smaller light hydrocarbons, but amongst these methods, photocatalysis is preferred since it only requires solar irradiation as an energy source and has been proven effective in multiple applications. Now, this is where perovskite oxides come into picture. They are already being used in many photocatalytic reduction systems for their good photoactivity, abundant nature, and their desirable band gap, which absorbs visible light. Based on this, here we present bismuth vanadate nanoparticles synthesized using hydrothermal method, which were tested for their photocatalytic efficiency by spray coating them onto glass substrates to form thin films and then integrating them with a planar microfluidic system for carbon dioxide reduction. Now this diagram here is a proposed mechanism for the photocatalytic carbon dioxide reduction occurring at the surface of bismuth vanadate nanoparticles. Here, under visible light illumination, an electron from the valence band of bismuth vanadate tends to jump towards the conduction band at an energy of 2.4 electron volts. This electron then interacts with the carbon dioxide molecule, which is anchored to the bismuth oxygen bond, and then brings about its reduction. For assessing the photocatalytic activity of bismuth vanadate, first the nanoparticles were synthesized using hydrothermal method. Later, they were characterized structurally, morphologically, and optically to identify the exact crystalline form of the nanoparticles. Then a planar design of the microfluidic system was developed using SolidWorks software, and the model was printed with resin with the help of a 3D printer. The nanoparticles synthesized were then deposited with the help of air spraying technique, and they were then integrated with the microfluidic cell to be further used for carbon dioxide reduction experiments. The the experiment was performed using 0.1 molar bicarbonate solution, which was allowed to pass through the microfluidic cell at a rate of 50 microliters per minute with the help of a syringe pump under visible light illumination, and the aliquots were taken at a time interval of 30 minutes, and finally the entire experiment was run for a period of 4 hours. Eventually the product generation and identification was tested using gas chromatographic studies. For the results, first step was to identify the band gap energy of the nanoparticles, and based on UV visible spectroscopic studies, we found that the nanoparticles show good absorption in the uh, visible light spectrum, and they showed a band gap energy of 2.4 electron volts, which is well reported in the literature. And with this confirmation, we then proceeded with the other characterizations of the nanoparticles. From the UV visible spectrum, we also calculated the band gap energy, and that was around 2.4 electron volts. FTIR studies also showed the vibrational modes of bismuth ion, oxygen, and vanadium tetrahedron. Also, the XPS spectrum showed the binding energies of bismuth, oxygen, and vanadium ions individually, which was again in uh, accordance with the binding energies reported in literature. To finally confirm the crystalline structure and the form of bismuth vanadate, XRD studies were performed, and when XRD diffractogram was compared with the JCPD card number for monoclinic scheelite form of the bismuth vanadate nanoparticles, we found exact match, and hence we finally could conclude that indeed the nanoparticles synthesized using hydrothermal method were of the monoclinic scheelite form of bismuth vanadate nanoparticles. Also, the nanoparticles were characterized morphologically using SEM, IDAX, and from the micrograph, it can be seen that nanoparticles were in the form of monodispersed nanoparticles and spherical ovoid nanoparticles. The nanoparticles deposited onto the glass substrates were also analyzed using SEM, and the micrograph showed uniform distribution and a uniform coat of the nanoparticles on the surface of the glass slide. To analyze the thickness of the deposition, profilometric studies were also performed, and from the profilometric scan it can be observed that a uniform deposition of around 2.3 micrometers was obtained. Hence, with this confirmation that the nanoparticles were indeed monoclinic scheelite form, and with the results of a uniform deposition of the nanoparticles on the glass substrate, we then proceeded to synthesize, to produce, to fabricate the monoclinic, the microfluidic cell. And after it was printed, the glass slides were integrated with the microfluidic cell, and photocatalytic carbon dioxide reduction experiments were performed. From the reduction experiment results, the results are displayed in these graphs. The electrolyte, before it was purged with carbon dioxide, it was tested using gas chromatography to analyze the presence of any contamination or the presence of any contamination basically, and it was found to be just bicarbonate solution. Later it was also tested after being purged with carbon dioxide, but still not in contact with the material, with the photocatalyst, and it again didn't show any presence of reduced product contamination. It was just bicarbonate solution with carbon dioxide gas. And eventually, after the bicarbonate solution purged with carbon dioxide was allowed to pass through the system with the help of a syringe pump, and after that, when the aliquots were taken and they were analyzed, we found the presence of ethanol as a reduced product in the reaction mixture, and this was observed to be maintained up till the first peak was obtained at the first aliquot that was taken at around at 30 minutes, and this obtention of ethanol continued till the 4th hour of the C carbon dioxide reduction experiment. Now, this could be there could be multiple factors which are facilitating the production of C2 compound instead of C1 compound. One could be the intensity of the lamp that was used. We were using a 20-watt lamp, but some reports have mentioned that intensity of the lamp, of the visible light source, can also influence the production of C2 compounds instead of C1 compounds. And Again, the photocatalytic nature of the material is the another factor. Here the bismuth anodate nanoparticles show the synthesis of the production of ethanol as a reduced product. Final conclusions: the nanoparticles synthesized using hydrothermal method. After characterizations, we were confirmed that they were indeed monoclinic scheelite form, and we were interested in monoclinic scheelite form because multiple reports have mentioned that monoclinic scheelite form is the efficient form to bring about carbon dioxide reduction as compared to the tetragonal zircon form or tetragonal scheelite form. Also, from the characterizations, all the peaks and all the binding energies and rotational modes, they were all directing towards the monoclinic scheelite form of the nanoparticles. Here we report the synthesis of generation of ethanol, and at a very low rate of 50 microliters per minute, as compared to another report which has reported the generation of C1 compounds, and that too at a higher flow rate of 200 microliters per minute. So we conclude that for this design and for this microfluidic system, lower flow rates are much more efficient than higher flow rates. And finally, the bismuth anodate nanoparticles, they indeed were proven to be an effective photocatalyst to bring about efficient carbon dioxide reduction in microfluidic systems. So that's it. Any questions, we can be reached at our email addresses, and thank you for tuning in.